Hello everyone and welcome back. My name is Mr. Cobalt and in this video I'm going to be going over limiting reactants. So what are limiting reactants? I think the best way to explain this is through an analogy where you're making peanut butter and jelly sandwiches. I picked peanut butter and jelly sandwiches because that's what I grew up as a child eating during lunch was peanut butter and jelly sandwiches. You could do this with pizza or bicycles or cars or whatever you want to use. I'm going to use peanut butter and jelly sandwiches, so bear with me. So, when you're making peanut butter and jelly sandwiches, you need three things. You need bread, slices of bread, peanut butter, and jelly, right? So, if you are in the process of making peanut butter and jelly sandwiches, let's say you want to make for a picnic. You want to make peanut butter and jelly sandwiches for a picnic, or maybe for the whole family, a get together, or maybe for a school event, or whatever the case may be. You need to make peanut butter and jelly sandwiches. So you can only make an as how do I phrase this? You can only make peanut butter jelly sandwiches as long as you have all three ingredients. As soon as you run out of an ingredient, you can no longer make peanut butter and jelly sandwiches. So let's say I have some bread and I got some jars of peanut butter and I've got some jars of jelly. So I start making peanut butter and jelly sandwiches. I need two pieces of bread. So, and then I spread on one side of the bread peanut butter, on the other side of the bread jelly, put it together, done. And then I keep going. I can keep doing that and making peanut butter and jelly sandwiches until something runs out. If I run out of bread, but I still have some peanut butter and jelly, I can't make peanut butter and jelly sandwiches because I don't have any bread. Or as I'm making the peanut butter and jelly sandwiches, I run out of peanut butter. I still have the bread, still have the jelly, but I don't have any peanut butter. So the process of making peanut butter and jelly sandwiches is at a halt. It stops, right? Same thing can be said about jelly. Like if I run out of jelly, but I have the other two items, I can't make any peanut butter and jelly sandwiches. So the idea here is that whatever ingredient I run out of first during the peanut butter making process will limit the number of sandwiches I can make. So if as I'm making peanut butter and jelly sandwiches, I'm making peanut butter and jelly sandwiches, right? So as I'm making peanut butter and jelly sandwiches, I run out of bread, but I still have peanut butter and jelly. In that case, the bread is the limiting reagent. It's the limiting factor. It limits how much peanut butter and jelly sandwich, how many peanut butter and jelly sandwiches I can make, right? So same thing goes for if I run out of peanut butter, right? So as I'm making the peanut butter and jelly sandwiches, if I run out of peanut butter, but I still have the bread and jelly, I can't make any peanut butter and jelly sandwiches. In that case, the peanut butter is the limiting reagent or the limiting factor that limits how many peanut butter and jelly sandwiches I can make. So it's the same thing in a chemical reaction, right? So if I'm given a certain amount of reactant A, and along with that, a reactant B, a certain amount of reactant B, I don't know which one will run out first. So I need to figure that out. I need to figure out which one is the limiting reagent because remember, the limiting reagent will determine how much product I can make, right? So if in my peanut butter and jelly sandwich analogy, I can only make as many peanut butter and jelly sandwiches as the ingredients will allow. So whatever ingredient I run out of first, that's going to limit how many peanut butter and jelly sandwiches I can make. That's the limiting ingredient. Okay. So with the chemical reactions, the limiting reactant will determine how much product I can make. In the same way that the limiting ingredient will determine how many sandwiches that I can make. I can't make any more sandwiches beyond what the limiting reagent dictates because I will run out first of whatever that limiting ingredient is. So that's the idea for a limiting reagent. So so hopefully that's clear. So how do I identify whether I have a limiting reactant problem or not? Well, that's easy. Whenever you're given a problem where they give you two substances, right? If you got two different amounts of reactants, right? Okay, so they give me like 50 grams of reactant A, they give me 75 grams of reactant B. How much product is formed? If you got a problem like that, that's a limiting reactant problem. And so just because I've given like less amount of one reactant doesn't mean that that's the limiting reagent. It doesn't mean that that one's going to run out first. It just depends on the equation and the reaction itself. Okay. So how do I determine if I have a limiting reactant problem? If they give me amounts of two reactants and they ask me how much product is formed from the reaction of these two amounts of reactants. And if that's all they give me, then that's a limiting reactant problem. I first have to determine which of those reactants is the limiting reactant. From there, I can determine how much product can be formed. Okay, so with that out of the way, let me also specify or let me also point out that just like with stoichiometry with a regular equation, right, where you're converting from one substance to the other, you have to use the same process for a limiting reactant. In this case, you're going to do it twice, right? Because we need to use this process to figure out which one is the limiting reagent. And there's a couple of ways you could figure out what the limiting reagent is, but I think the most straightforward way is to just take the amounts of both of your reactants and convert it to product, right? So take reactant A, take the amount of reactant A, figure out how much product can be formed from reactant A. Then do the same thing with reactant B. So if I'm giving kilograms of reactant B, I'm going to convert that to kilograms or grams or whatever the unit is. I'm going to convert that to that unit of product. And then I'm going to compare which reactant gives me the lesser amount of product. If whatever reactant that gives me the lesser amount of product, that's the limiting reagent, because remember, whatever reactant gets used up first, that's going to determine or limit the amount of product you can have. So if one reactant gives you a smaller amount of product, then that means that that reactant ran out first and therefore limits the reactant to that amount of product. You can't get any more from that reactant. No matter if the other reactant says, hey, I can get more. Well, no, you can't. Because that reactant that you can get more product from depends on reacting with the other reactant that gives you less. Okay, so I'm hoping this is clear. I'm going to do a couple of examples to help clarify this. Okay, so here I have a problem. I have my balanced equation, and I'm given 550 moles of Si2 silica, and I'm given 1,000 moles of carbon. And I'm asked, well, what's the maximum amount of product I can form, in this case, silicon, from this reactant of these two amounts? Okay, hold on a second. Sorry about that. So what am I going to do? So in order to determine which one of these is the limiting reactant, I have to convert both of these amounts to the amount of product both of these are going to give. So that's the first thing. So I need to use my roadmap. So I need to figure out how much silicon is going to come from this amount of SiO2. So let's do that. So I have 550 moles of SiO2. I'm going to put that over 1. So this is going to be a simple conversion because according to the roadmap here, so I have substance 1, my silicon dioxide, it's in moles. So I'm already here. I don't need to convert anything. I've got moles of substance 1, and then I can convert that to moles of substance 2. So all I need is the mole ratio between substance 1 and substance 2. So that's going to be the mole ratio between SiO2 and Si. And we can see here it's a 1-to-1 conversion. So for SiO2, that's going to be 1 on the bottom. So 1 mole of SiO2. And then I'm going to have Si on the top. So 1 mole of Si. So moles of SiO2 cancel out. And of course, 1 times 550 is going to be 550 moles of Si. So 550 moles of SiO2, if this was to react completely and all of this was to be converted into Si, I would get 550 moles of Si. Okay, now I have to do the same thing with carbon. So what would happen, how much Si would I get if all 1,000 moles converted to Si? Well, let's find out. So I have 1,000 moles of carbon. And again, because carbon is my substance 1 and I have moles already, so all I need to do is use the mole ratio to convert moles of carbon to moles of Si. So in this case, I have 2 moles of carbon to 1 mole of Si. So the 2-to-1 mole ratio. So 2 moles of carbon on the bottom and 1 mole of Si on top. So moles of carbon cancel out. Now I have moles of Si. So 1,000 divided by 2 gives me 500 moles of Si. So now I've converted both of the given amounts of reactant to the desired product Si. Now, what do I have here? Basically, if 550 moles were to if 550 moles of SiO2 were to completely react to give me Si, I would get 550 moles of Si. If all 1,000 moles of carbon were to completely react to give me Si, I would get 500 moles of Si. Well, the amount of carbon that I have that they gave me can only give me 500 moles of Si. I only have enough carbon to give me 500 moles of Si. I have enough SiO2 to give me 550 moles of Si, but I'm going to run out of carbon first because it's going to give me, I only have enough of the carbon to give me this amount. Once I produce 500 moles of Si, I know, excuse me, I no longer have any carbon left. It's gone. So then that means I'm going to have an excess amount of SiO2 left over, just like in the peanut butter and jelly sandwiches example. If I run out of bread first, I'm going to have peanut butter and jelly left over. And so even though I could make more sandwiches with the peanut butter and jelly, I'm not going to be able to because I ran out of bread. So you can think of carbon as the bread running out before the peanut butter and jelly. So therefore, according to this, because I produce less Si from the given amount of carbon, carbon is my limiting reactant. So carbon would be the limiting reactant. Let me use a different color. So this would be limiting. And so if this is my limiting reactant, then this tells me that this is the maximum amount that I could produce. I can't produce any more than that given these amounts of reactant. And that, ladies and gentlemen, is how you figure out what your limiting reactant is and how much you're able to make given that amount. Okay. So I want to continue with another more difficult, not difficult, but a more involved problem. Typically, you might be given a mole to mole conversion, but typically you're given a mass to mass conversion. So if I change this a little bit, let's go from mass to mass and see how that works. Okay, let's say we're given, well, what's the amount I want to use? 16,491. So let's say we're given 14 or 16, what's the amount? 16.491 grams of carbon instead of moles. And then for the SiO2, we're given 32,654. So 32 grams and 654 grams of the SiO2. Okay, so now instead of moles, we're giving gram amounts. So this is typically what you're going to be given in this sort of problem. So you're given gram amount of one reactant, a gram amount of another reactant, and you're asked, well, how much product is produced? What's the maximum amount of product you can get from this mixture, this reaction? Okay, you do the same exact thing. You need to take both of the gram amounts of each of your reactants and convert that to product and see which one gives you the lesser amount of product. Okay, so let's go ahead and erase this and we'll start over with the mass amounts that they gave us. Okay, so again, I'll start with 16.491 grams of carbon. And now, again, in this case, we got to follow the roadmap. And so we'll need to convert grams. Here we're starting with grams. We'll have to convert that to grams of substance too. Usually they want you to convert to the mass of another substance. So we'll do that with both of the reactants. We'll take the first reactant, convert it to grams from grams of that substance to grams of the product. And then we'll do the same thing with the other reactant and see which one gives us the lesser amount. So we're going to set up our conversions. So I've got carbon here. So 16.491 grams of carbon. I want grams of carbon. On the bottom, I'm going to use the molar mass to convert to moles of carbon. So I have 12.011 grams of carbon on the bottom and 1 mole of carbon on top. So grams are going to cancel out. Next step, I'm going to convert moles of carbon to moles of silicon. And again, it's a 2 moles to 1 mole. So I got 2 moles of carbon on the bottom, and I'm going to have 1 mole of Si on top. So moles of carbon cancel out. And then I can use the molar mass. So now where am I at? I went from grams to moles of substance 1 using the molar mass. Now I went from moles of substance 1 to substance 2 using the mole ratio between the two. And now to get to grams, I'm going to use the molar mass of silicon to convert to molar 2. And the moles of silicon is 28.055. So 28.055 grams of Si on the top and 1 mole of Si on the bottom. So there's my steps. Grams of carbon to moles of carbon to moles of silicon to grams of silicon. So moles of silicon cancel out and I've got grams. So now all I need to do is calculate the amount of grams. And so when I calculate the amount of grams of silicon, I get 19,281. So this is equal to 19.281 grams of silicon. So again, if I react all of this carbon, 16.491 grams of carbon, if all of this reacts, then this will give me 19.281 grams of silicon. Okay, now let's look at the SiO2 amount. So they gave us 32.654 grams of SiO2. So we're going to convert that. We're going to do the same steps. We're going to convert that to grams of silicon. So let's go ahead, 32.654 grams of SiO2 over 1. So again, first step, grams to moles. I'm going to use the molar mass of SiO2 to convert that to moles. And oops. Sorry about that. So I'm going to use the molar mass of SiO2 to convert to moles. So when I look that up, 60.0843. So 60.0843 grams of SiO2 on the bottom and 1 mole of SiO2 on the top. So now I got moles. So again, I'm going to use the mole ratio between SiO2 and Si. So it's a 1-to-1 ratio. So I'm going to write that out. So I have moles of SiO2 on the top. So I'm going to put 1 mole of SiO2 on the bottom and 1 mole of Si on the top. So moles of SiO2 cancel out. Oh, I forgot. Grams of SiO2 are going to cancel out grams of SiO2. And finally, now that I have moles of SiO2, that's moles of substance 2. Now I'm going to use the molar mass again to convert to grams of Si. So again, this last step here is the same. So I'm going to write it down here because I don't have room over there. So again, 28.055 grams, 28.055 grams of Si on the top, and then 1 mole of Si on the bottom. So moles of Si on top cancel out with moles of Si on the bottom. And now I have grams of Si. So now all I need to do is multiply across the top, divide by the bottom, and calculate how much Si is formed. And when I do that, I get 15,264. So 15.264 grams of Si. So now I'm looking at the amount of Si that was produced by both reactants. This is assuming that both reactants go to completion. So if I react completely 16.491 grams of carbon, it will produce 19.281 grams of silicon. If I react 32.645 grams of SiO2, that will give me 15.264 grams of silicon. So this is the maximum amount of silicon that I can get from this amount of silicon dioxide. This is the maximum amount that I could get from this amount of carbon. Notice that this amount of silicon dioxide can only give me this amount here. This is the lesser amount. So once I produce this amount, I no longer have any more SiO2 left. So all of this is gone. So from this amount of SiO2, this is the maximum amount of Si I can get from this amount. I can't get any more. It's like I ran out of peanut butter, right? So once you run out of peanut butter, you can't get any more peanut butter jelly sandwiches. So this, ladies and gentlemen, is the maximum amount that I can get, which means that in this case, the SiO2 here is limiting. So the SiO2 is my limiting reagent, and this is the maximum amount of product I can get from this reaction. So I hope this was helpful. If you enjoyed this video, if this helped you understand better limiting reactants, and if you learned from this video and if you enjoyed this video, then please, by all means, like the video, share the video with your friends and family. Hit that like button somewhere over there, I think. Also, make sure you subscribe to my channel. Hit that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. And then finally, put a comment down below in the comments section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question you want me to answer or a problem you want me to go over, please put that down below. If you have a topic you want me to cover, go ahead and let me know below, and I would love to do that for you. Thanks for joining me, and have a great day.